the world is vast, and mathematical representations are complex. So there's actually a lot we can do. But I wanted to make sure we cashed out. We actually talked about the basic math that we had sort of been using so far. We'd sort of relied on your past experience with arithmetic to handle things like addition, subtraction, division, multiplication, assignment, etc. But to review, these are the operators. These are technically binary operators, meaning they have a value on the left hand and the right hand side. It takes two values to make addition work, and subtraction, division, multiplication, and assignment. Right? And there's an order of operations here. You've probably seen all those like social media posts where like some people think the math goes one way and other people think the math goes the other way, and they argue about it a bit. It's pretty prescribed in programming here. You go from left to right. Multiplication, division happens before addition, subtraction. So you can get like a flip for the value of A here, right? What do you think the value is? Yeah, 15. Right, so you want to follow this interval of operations, the value is 15. So you all have a good handle on this. I'm confident that if you had good enough grades to get through your K through 12 education and you got into the UC system, you're doing fine on this front. But we're in a programming environment. We are in JavaScript. We have this bit of arithmetic dispersed through all this code, through all these other textual objects on our screen. And we're not just limited. Our variables aren't just limited to numbers, right? They can be whatever we give them. They can be strings. They can be numbers. They can be Booleans. We went through all this earlier in class. So what happens if you accidentally mix them, or something goes awry with your numbers? Well, we can handle some of it. Like we have some rules for this. So 10 and 20 can be added together because they're both numbers, right? But if you add 30 plus the string 30 together, it actually doesn't work because the right-hand side thing is a string. Now, JavaScript, in some cases, can handle strings as numbers. So if you had the example here where x is 100 and y is 10, and you divided x by y, it actually tries to interpret the strings as numbers and then use them numerically. This is pretty inefficient. Like if you did a lot of math and all of your numbers were in string format and they all had to be converted every time you used them, that's a lot of extra juice that your machine would have to pull off. A lot of memory usage, a lot more cycles, not very efficient. So this can happen, that this is a case that you could be in, but it's not a case you want to be in. There's also, yes.
Sorry.
Yeah, go ahead.
Is it any similar to like how spreadsheets do their own math, like Microsoft Excel?
Yeah, so spreadsheets, Excel, Google Sheets, all of these face these same problems. They may have different rules for how they react to these situations. Each programming language treats these things a little differently. So you want to look at the rules of JavaScript for these things and not assume that everything works like Excel, but having the intuition that, hey, I can't really mix these two things well in Excel is a good intuition to have because it sort of like lasts across programming languages. So there's not a number. You may have encountered this one. NaN. So if you do something like divide 100 by the string apple, it has no idea what to do, right? In that case, it gives you something back. It gives you a special type called NaN, or not a number, right? It's something that all that we know about this thing is, hey, it's not a number. That's all we know about it. And all not a numbers are the same. As soon as you get some result that can't be, that is in sort of a mathematical setting, has arithmetic operators involved, and can't be resolved into a number, you get not a number. We also have infinity. If you divide something by 0, it'll be infinity in this case. You can also count up to infinity. If you go and keep, in this example here, where number is 2, while my number is not equal to infinity, take my number and you square it. Eventually, you're going to get past what a number can hold, the maximum value that can be represented by numbers in JavaScript. And once you get past that point, it's like, hey, that's infinity to us. We can't count higher than that. So now your number is infinity. And just like not a number, infinity is like a special type of thing that's returned, which can't really be intermixed with math. It's a signal for you as a programmer, something you can actually test against. You can see if a number is type of not a number, or if number is type of infinity. So you can actually check to see when you're in these states. But most often, particularly for this class, you'll probably see an error message happen in the console below. They'll be like, hey, this number's infinity. I can't use it for math. Or, hey, argument 2 expected a number, but you gave me not a number instead. Right? This often happens when somehow you mess up the math somewhere along the line. I'm curious, how many of you have seen not a number so far? Okay, 1, 2, 3, 4. Okay, a few of you. 5. So you should be aware that these exist. These are in our world. We're not going to go too deep into them now because we're more interested in learning the basic capabilities of programming, but these will come up and we'll just handle them as we need to in class. If you're curious about them, there's lots of documentation about not a number, about how strings intermix with numbers, and about infinity. I'm happy to provide that information if you're so curious. Just let me know. We have some short forms for math. Hopefully this will be a bit of review. I think we've talked about most of these. There's plus plus, which is a unary operator, meaning that it only takes one number to operate on, the number to its left-hand side. So a plus plus is equivalent to a equals a plus 1. A minus minus is the equivalent to a equals a minus 1. Now plus equals, that's an interesting one. This is actually pretty handy to use in your the update part of your for loops. A plus equals 5 is the same as a equals a plus 5. A little syntactic sugar. And you can do minus equals, times equals, divide equals. All of them work in this case. Any questions about these? Because you're all learning and are all doing so well in the class, there will be no questions, I'm sure. This class is doing so well. It's great. What happened? No. Get back to your slides. Okay. Now we've looked at this a little bit. We looked at this in the alternating grid example in class the other day when we talked about iteration. There is a ampersand operator, the and sign, or the percent sign. Not ampersand, it's percent sign. What am I thinking? Long day. A lot of emails to senators today. It's called the modulo operator. And you sort of read it as A mod B. That's how you'd say it out loud when we were talking. So it's basically, it gives you a remainder. So you divide A by B, and the result is the remainder. So 14 mod 3 is 2. 4 mod 7 is 4. And you have some guarantees. So you know that the result is always going to be less than that second number, than B in this case. So C is always going to be less than B. Because if C was equal or greater than to B, that wouldn't be a remainder, right? You didn't do your division right. Your division did not happen correctly in that case. So this is really handy. Like we talked about how to check if something is even or odd. You could get some random number and see if it was a coin flip of yes or no by modding things by 2. There's all sorts of interesting uses for mod. You want to count up months and see what year you're in? You can do that as well, particularly if you have your own like little Sims world. Angles. So trig is handy for us with graphics and motion, circles, coordinate systems. But we know that natively, or by default, P5.js works in radians and not degrees. We have a couple ways to fix this, like we talked about in class before. We have the radians function, which converts degrees into radians. There's a degrees function, which does the opposite, converts radians into degrees. We have our angle mode function, which we can set 2 degrees, radians, etc., which will change the default behavior, or the behavior of how the calls to things that take rotation, that take angles, are interpreted. It's very handy. Review, 2 pi radians is 360 degrees. 1 pi is 180, or just pi is 180. There are a few constants for us. There's pi and 2 pi. Those are values that you can just use. That'll give you the highest resolution pi and multiples of pi values to use. But in short, if theta, or the common Greek number representation of an angle in trig, is in radians, you can just use it right away without changing anything. But if you want to work in degrees, we need to either convert degrees into radians or use angle mode degrees to say, hey, we're working in degrees globally instead of radians. All right. That was enough review, right? We've talked about this a little bit. Let's look at cosine theta. So today, look at all those lab fours. Look at all those suns. Okay. We have some examples today. We're going to start with the one on the right here, called sine theta. All right, and this, as you can see, let's do the big version, is a visualization of sine and cosine. We made these lines ourselves. Let's see how we did it. So first we define some colors. I've been using this color scheme for this section of the class. It's Goldfish by Mane Kineko. You can see the link here. AoE, clean pond water, and beach storm, giant goldfish, and unreal food pills. So their values here. Creating a canvas, setting stroke weight to 5, setting the background color to clean pond water, setting the stroke to giant goldfish. And now we have some scales. Basically what we're doing here is we're taking the output of sine and cosine, and we want to transform it to some representation on the screen. Right? And in this case, we can scale it up. We can scale it vertically. So this is for us to be able to control sort of like the length and the height of these waves to be able to fit it onto the screen. We have the 0 line. So it's 400. This is a 400 by 500. But no, the changes didn't save. I had it prettier earlier. It was 360 by 360 with a 0 line of 180, and it made everything line up perfectly. We're a little imperfect right now. But the 0 line is where 0 is on our graph, so right in the middle of the waves. We have our previous x and previous y. So what we're doing here is we're just drawing a bunch of lines that connect each other. And so we're basically doing the same thing that you would do in calculus, right? You're approaching the limit of the difference between points on a space. This is how graphics work. Like if you zoomed in on this, you'd actually see a bunch of small lines. It would look jagged if you zoomed in close enough. And this is the case for lots of 3D graphics. How many of you have ever seen like a wireframe of CG where you just see the lines around it? Right? I'm sure a lot of you have seen this over the years. Yeah, so you can see that's the primitives. Those are the actual vertices and edges that we're working with, that things are constructed of. But we do things like fill in the surfaces, and we do things like smooth the edges with anti-aliasing techniques to make things look more round than they actually are. In this case, we're working at a fine enough grained level, and the stroke width is wide enough that you don't actually see a lot of the jagged edge. Actually, if you came up here, you can actually see them if you're up close enough. Look, it's really blown up. Okay, so what we're doing here is we're going through and we're calculating the next x and y value to show where the next points in sine and cosine are. So first, we're starting with cosine. And we're going through for all 360 degrees. We're going through and we're drawing one small segment of that wave. And because line takes a beginning point and an end point, what we're doing is looking at the point we just generated and the point that was generated previously. And those are our two endpoints in our line. So we're connecting them together into a wave. And we do the exact same thing for sine. What do you think? This sort of thing makes sense? You have any questions? You can do all sorts of things like this on your own. So angles are great for us. Trigonometry is great for us. It's a powerful tool. And we'll use it again later. We'll show some more examples. But what I really like and what I think is pretty exciting about this is pseudo-random numbers. So a quote from the famed computer architect John von Neumann. Anyone who considers arithmetical methods of producing random digits is, of course, in a state of sin. What do you think he means? I'm sure he wasn't talking about the demonic qualities of Dungeons and Dragons with rolling dice. What was he referring to? It also is linked to why we call them pseudo-random numbers and not random numbers. Yeah?
Is it because by using arithmetic, it's just like a really long pattern, so the most it can be is a long repetition?
Essentially, yes. You cannot achieve true randomness in a machine that is deterministic at its core. Right? Where's the source of randomness coming from? We have nothing that's truly stochastic in this machine. We can have things that are complex enough that they appear to us as humans as random, but that's a different story, right? So this is why in computers and in games, you never see like truly random values. I'm sure you've all been frustrated in your games by RNG. But essentially, it's an algorithm, a formula for generating a next number. And that's all we really have to work with. Now, we can find some true randomness out there, and there are some places where you can computationally access true random. The National Institute for Time and Standards, or Standards in Time, NIST, has a sensor hooked up to atomic decay. And you can go to a website, call an API, and look at the current value of that atomic decay and get a source of randomness. If you wanted to go full in, true random, there are ways to do it. But it's not going to be on your machine. So this is a source of strength and weakness for us. So this is where I want to introduce random. So let's look up the random function call. We don't need this right now. p5js.org. And we'll go and look up random. So here's some examples for us. Get out of here. We have a random function that's built into p5.js that we can just use. So it's kind of neat. So if you call random without a parameter, it'll give you a number between 0 and 1. That's kind of neat. It's good for lots of things for us. You can also give it two values, something like 1 and 10, and it will give you a number between 1 and 10. If you just give it one number, it'll give you a value between 0 and that number. You can give it negative 10 and 10 and get a number between negative 10 and 10. Shock and awe here. Now, what's really interesting about this is that we have lots of ways of controlling this. And we'll get to that in just a moment, but this random is very handy. Let's look at the raindrops example. Pastel raindrops falling on a wet pond. Blobs of pastel watercolor falling on a canvas. We're using random to pull this effect off. So we have a 6x600 canvas. Background is white, frame rate is 20. We can change the frame rate to speed up the drops or slow them down. We're setting a stroke color to a slightly transparent gray. And we're in our draw function. So the first thing that we do is we use random. Random 1, in this case, is the same as calling random with no value. It'll give you a number between 0 and 1 with a decimal. So we're assigning that to this variable called pick. So we're picking from, we're choosing from, we're sampling from a space. So if the pick is less than 0.5, we set the fill color to this. Else, if the pick is less than 0.7, so now it's greater than 0.5 and less than 0.7, we have a slightly lighter fill color. Otherwise, so this means if pick was greater than 0.7 and less than 1, or less than or equal to 1, then we have this final fill color, which is a translucent white. And then we get a little random number between 0 and 40, and we use that for the offset for height and width, for its size. And then we also randomly place it. We call random height and random width, which is the width and height of the screen in this case. And the result is this. Now you can see where roughly half of the circles of the drops are this a purplish color. About 20% of them are the pink color, and then about 30% of them are white. And because they're all using transparent stroke colors, they pattern on top of each other and intermix. So I think that's a neat little effect. And we get that with, only 30 lines of code. And it's fairly, I think, straightforward code at that. Do you have any questions on this? What do you think? Yeah.
Because I remember we covered this in a previous lecture. What does the numbers between 0 and 1 represent again?
They are just numbers between 0 and 1. You use them however you want. They're just values. It's how you interpret those values that matters. And here we're interpreting them as a color pick.
What about the 40? What is that?
Yeah, that gives us a number between 0 and 40.
Oh.
Yep, and that's so we're adding that to the width and the height, the base width and height, which is 44 for each one of the circles to make each one of them a slightly different size. Any other questions? Oh, yes, go ahead.
Does it account for like smaller integers like 0.5, 10.5 and like stuff in between like decimals?
Yeah, I mean, that sort of gets discarded at the pixel level, right? Because things can't be fractions of a pixel. So it just kind of lost there. But you can force things to be integers. There's a certain option to do that. Usually you call either floor or ceiling, which will chop off the decimal point or raise it to the next point if it's a fraction. Raise to the next whole number if it's a fraction. So you have ways of generating actual numbers on this. And when we get to the end of class, if we have time, I was wanting us to look at the sprite animation example, and I use that there because they are fractional like fractional things that compound over time that aren't exact whole numbers causes a problem. All right, any more questions about raindrops? All right. So random's our friend. I really like random. Random will help you out quite a bit. Now, random isn't the only way to produce values. We also have noise. How many of you are familiar with the movie Tron? Right? What was a technically amazing thing about Tron?
The graphics.
Yeah, it broke ground on computer graphics. Did you know that part of its technology won an Academy Award? Ken Perlin won an Academy Award for this function, for this noise function. It has properties that are very interesting and lead very well to art. If you've ever seen like generated clouds or smoke, likely somewhere in there at its heart is a call to noise. Perlin noise, to be specific. So Perlin noise is great. What it does is the smaller you give it, you give its parameter, time in this case is how it's interpreted, the lower the value of time you get, the closer the output is to that number. So if you had like time equals 1, if you called it twice, one with time 1, one with time 2, you get things like that are like this, that are pretty far apart. But if you give it like time 1 and then time 0.1, the values would be pretty close to each other. So the change of values that it produces when time changes is a little more continuous. Whereas with random, you don't know what the next value is going to be. It can be, one can be -1, the other can be a billion, right? You don't know. It's more true, more pseudo-random. This is more of a controlled, continuous, but still unpredictable space. And it can be used in any dimension. You can have 10-dimensional graphics. You can do, what's the 4-dimensional exploration game? Amagakuri? I'll have to look that up, but we'll talk about that later. And you can control the detail that you get from the noise with the noise detail function. So you can see how big and sweeping those continuous changes are with respect to time. So in another sense, it looks like this. So Perlin noise, when you increase time, it does change and it does oscillate, but it still kind of respects the points before it. Whereas with true random, it's all over the place. There's no like really predicting it or working with it. There's no continuous nature to it. So to recap, noise returns a value between 0 and 1. You must increment that value to get a different value from it. So if you keep giving noise the same value, you'll keep getting the same value out of it. Small increments, the values will change slowly. Larger increments, it'll change a lot. If you get big enough values, it'll just seem like random. I also wanted to note that we did this in raindrops. This is important for us to know. So if you get a random number R, oh, this should be let, not float. One got by me. That you can use this as a choice mechanism. Let's say you have an orc warrior attacking an elven archer, but the elven archer has a 30% dodge chance. This is where you'd roll on that dodge table. You get a value between 0 and 1, and if R is less than 0.3, you dodged. Otherwise, you got hit. Right? So you can start building hit tables from these things. You can start making choices. You can make a table of possibilities and then roll random to help choose from them. And you can weight the values of those tables. If, let's say, the elf gets higher agility score, you can have its dodge chance of 30 plus its agility as part of the random space here. And that will help bias the table. It'll help make the outcomes a little more or less likely. Right? So this is a good dice roller, good randomizer. Now, this is sort of an aside for you. I encourage you to go into raindrops, the raindrops example, and change the ellipse call to this thing in the title, this call in the title. And if you can explain to me like your goal should be to explain like why, like what changed and why it changed. So if you want to dig a little deeper, or if you're a little curious, or if you don't think you understand it, this would be a great way to test your knowledge. How many of you have played Minecraft? What's a seed? What's a seed in Minecraft? Yeah?
It like determines like the landscape of the world you're in.
Exactly. So can you give a seed to a friend? What happens if you do?
They get into the same world.
They get in the same world, right? This is because Minecraft is using random, just like we're using it here at its heart. So what if you give random a seed value and you call random a bunch of times with that seed value, you'll get a sequence of numbers. If I give you that same seed value and you put it in your program and call random a bunch of times, you'll get the same sequence back. This is really neat, particularly for generative art. When you make something like a generative tree or a generative poem, something that has random and random is used regularly in its core, you can essentially save that picture by just knowing what its seed value was. And then you can give that seed value to someone else and they can generate the same picture as long as they have the same algorithm. So this is pretty neat, right? Like obviously Minecraft takes this to an extreme, right? But at the core, like a bunch of games that you've probably played use this. Like Hades, if you've ever played Hades, or coming up Hades 2. I'm looking forward to playing not the pre-release of that. They all have random and seeds at their cores as well to generate new levels and new parameterizations for what you do in play. If you've ever seen like procedurally generated trees, those are pretty popular. They can do the same thing. So random and seeds are powerful tools for computational media, for media computation as well. It's kind of neat. There's one here that you use the noise. There's one here that you use the random. So if you use Perlin noise and want to share seeds, you want to make sure that you set the noise seed value. If you want to have just with a random and get the pseudo-random values, you can set the random seed value. And these take just a number, an integer, a whole number. If you use random without a seed, it actually calls random to get a seed for you. So it'll randomly seed your random number generator if you don't pick if you don't set noise seed or random seed at the start. So we got stuff. Building tools, broadening our toolkit. Okay, well here's an example of noise. So we're going to look at this program in a moment. Why don't you take a look at this and see if you can think about what's going on here. So we're in our draw function, we're setting a background color. We are getting a value from noise, getting a value from it from time, which is a variable that we're managing. And we're multiplying that by width because we know noise gives us back a value between 0 and 1. All right, so now we're getting some scaled 0 and 1 value back from noise. Awesome. We're going to increment time because we need to change time. We're just going to get the same value back all of the time. We're going to set a fill color and then draw an ellipse. But our ellipse size is n by n, which is our noise value that we generated times height. What do you think is going to happen here? Let's find out. With the Perlin noise example. See how we're getting some sort of random-ish change in the radius of the ellipse? But it's not a sharp change. It's like just scaling up and scaling down like this continuous animated way. That's what noise does for us as opposed to random. Now, I'm going to slow this down a bit. I don't want to bust everyone's eyeballs. Let's make it a little slower. So now you can see each frame. You can probably notice the frame rate because the frame rate's 12. So you can see each individual sort of like change when it changes more dramatically. But you can see the value of the width is always pretty relative. We're pretty close to the value it was in the previous frame. Now what we're going to do is we're going to use random instead of noise. I'll play this for you and see if you can tell me what the difference is. All right, I know that's a lot of flashing, so I'm going to stop it now. What's the difference? What happened? It was certainly not the same, right? What do you think? Yeah.
Obviously, it wasn't as smooth. It was a lot more rough.
It wasn't as smooth and it was as rough. Okay. Yes, absolutely. Can someone help refine that statement?
The growth in diameter wasn't as like gradual, like it was more static in a way.
Yeah, it was not as gradual, was more static in a way. That we're starting to better characterize it. You rolled the ball forward. Yeah.
The next random number for the diameter chosen isn't random relative to what the last one was. So it could be like anything instead of within like, I forget what the margin was. But let's say like the margin was 1 to 5, it's not within 5 of it, it's within any number.
Exactly. Yeah, well done, right? So this is what noise gets us. This is the whole point of it. This is why we care about continuous values. We care about close values when we have small changes in that time or the time value or the value that we put in to noise. It helps us have more smooth choices. Like if you were using this to generate hills or terrain, you would want something that is more smooth and continuous to get rolling hills and terrain like we have in the real world due to erosion and things, rather than terrain that just spikes randomly in all sorts of ways and places. Because I'm selfish, I want to watch the smooth one again. Right, a little more satisfying. And I did do some research and tried to pick, since we're going to oscillate and flash a lot, pick color combinations that were less likely to flare up any people that are sensitive to flashing. All right, so this is what this code does. Like this is the power of per lin noise. Now, how many of you have worked in polar coordinates in geometry, algebra, any sort of graphing class? Okay, 2, 3 maybe? Maybe you kind of worked with it, but you're not comfortable with it and you barely remember what the heck it is? Is that more of what's going on? Yeah, probably. Well, we're used to working in grids, in a Cartesian plane. Well, in our case, a Cartesian plane with an offset inverted y-axis. But still, we're working on a grid with an origin, with an x-plane and a y-plane. So it takes 2 numbers for us to specify where we are relative to that origin, which that's how you position something. We need to know where we are relative to the top left of the screen. We don't really have like a galactic origin we can use. or a universal origin, so we make do with a local one. So in this case, we know how far we are from the origin in the x direction, how far we are from the origin in the y direction. Simple coordinate stuff like you've done a bunch of times. Now polar coordinates. They specify sort of like this system that relies around like circular, that rely around circles and arcs. All right. So we could also specify where we are given theta, given r and theta. So r is how far are you away from the middle, and theta is how rotated you are from its 0 point, right? So here we have this theta that maps us down a little bit. So we know where we are with r and theta. So like if we had r and 180, or if we get if this is r, if we had r divided by 2 and 180, the point would be like right here. Right, so we're just having a different way of encoding where positions are. So r is the radius from the origin, and theta is the angle from the axis. That's kind of neat. So polar coordinates are useful when you're working with circles. When you want to describe a circle as your root thing you care about, instead of like always going to calculate cosine x and or sine x and cosine y to find out where you are in the circle and converting polar coordinates to Euclidean coordinates, you can use this more compact, more appropriate representation of polar coordinates of r and theta, right? And so it's great to specify where you are from an origin. And this is for games like Euphoria. How many of you have played Euphoria? The classic indie game from like 2012. So it's all about you capturing these little planets as seeds. You are seeds in this game. And you take over planets, you plant your trees in them, and then they produce more seeds. And then you go out to try and capture more planets, and there are evil seeds out there that you have to defeat with your seeds. But each planet is an interesting little spherical object where a lot of action happens. Right? So each planet it's really handy to think of it in polar coordinates, or otherwise the math would just become quite intense. But now here you can think about like theta and r. So if r was just the distance from the middle of the planet to the surface, you just use theta to see where you are on that surface. So now this tree here, like this tree right here, is probably like theta 6, there's r 60. Right, and so now you can just, every time you go around the circle, everything is just r plus whatever theta it is that puts you around the radius of the sphere. Or puts you around the surface of the sphere. Or circle in this case. Right, so this is kind of neat. It's very handy for things like making like little planet simulators, making radial art. It's kind of handy. If you want to like make your own spirograph implementation, which is kind of a popular thing to do. A lot of people like making spirograph type of things in P5. Polar coordinates are a great way to do that. And play Euphoria, it's really fun. But you can also convert polar coordinates back to Cartesian coordinates with a pretty simple formula. You get the x value by taking r times cosine of theta, and you get the y value taking r times sine of theta. Right, so what's great is you don't have to just be in one representation or another. You can flip between them and use the best tool for the job at hand, for the task at hand. Okay. These are all like informational things that I'm hoping will help you bootstrap your projects later. But things like just understanding the basic definitions and the difference between Cartesian polar coordinates and like how to convert them. Those are all like things that could be on a midterm. Maybe not super important, maybe not a super amount of points, but they could appear. Now let's take a look at noise just a little more from another perspective. How many of you know what this sort of thing is? You seen a graph like this before?
Is that like decibels or perhaps like frequency range?
It is a type of graph that is used for those applications, yes. What is the type of graph? Go ahead.
Bell curve?
Sorry?
Bell curve?
Oh, a bell curve. This is a bell curve.
Oh, it's
But this graph has a bunch of areas and then values for those areas. Yeah?
Is it in equal
Nope, that's still an application. Yeah, I like where your mind is, though. Ah. Yeah,
A histogram?
it's a histogram, right? So a histogram breaks the world down into little chunks and fills those chunks with how many things fit into that bucket. So I often give out histograms of grades for my classes to show you how many people got an A minus, B plus, B minus on like an exam, right? And so if there were 4 people who got an A, the line that represented A would be 4 tall. And then we get like, 8 Bs and like 4 Cs, right? So it gives you an idea of relative fullness of each one of those categories. So here, we're going to actually look at our noise functions with this to see what we can find. So in this case, like if we have a graph that looks like this means the noise is biased around 0.5, right? It's highest. Those bars, the black bars are highest right around the middle of the graph, right? And this is sort of like a bell curve, like it had been mentioned. Right? Very few things on the edges, and most of the actions clustered around the middle. So let's look at noise distribution. So we're building a histogram on the fly here. Does this look like a bell curve, roughly? Where's the center of action here? Where are the values highest? In the middle or on the edges? In the middle, right? That's because we are using noise to get values. So basically what we're doing is we are calling noise a whole bunch and we're sticking it in buckets, and then we are visualizing those buckets with lines. So there are 100 buckets on the screen from 0.1. The first bucket is 0.0 to 0.1 value. The next is 0.1 to 0.2. The next is 0.2 to 0.3, all the way over to 0.99 to 1. To 0.99 to 1. Right? So each hundredth of this 0 to 1 space, we're making a bucket. And then when we call noise, we're just putting what came back from noise into the bucket. So again, we're filling buckets. It looks like 0.4 is ahead. 0.5, 0.6 catching up. The more you sample it, the more it will look like a bell curve. And where do we center around 0.5? Now, what do you think will happen if we replace noise with random? Get the values of random back and put those into buckets. How do you think this will change? Do you have a hand up? Yeah, good. I don't have to tell if you're resting or hand up.
There's a less standardized shape.
Exactly, the shape would be less standardized. I'm sorry?
Those things.
Okay, anyone else? Let's find out. Where is it strong? Where is it weak? I think the answers are everywhere and nowhere, right? Because it's a much more uniform distribution across the space. So we have time, which we had a noise with time, which made a bell curve. We have random here, which makes everything flat. So that's sort of like one of the key insights to why when you use noise, you get something continuous back, because you get something that's clustered around a center. Much more continuous in its space. Fade to black. The Gaussian dissolve. So one more time. We have our time distribution, which may look funny off the beginning, right? It hasn't had enough samples yet. The randomness is sort of pushing over to one side, but eventually with enough samples, it'll start filling out. Ooh, we got some RNG here. Someone's like got a bunch of crits when they shouldn't have. Oh, and someone failed some saving throws. But random's neat. Noise is neat. It gives it a lot of tools to work with. And it can help us make interesting decisions for us. It can help us with computational creativity. It can help, we can write some general things, and then it can explore a large space of possibilities for us. All right, that was noise distribution. Oh, we weren't supposed to have Kintsugi on here. But we can use our trigonometric functions to do some interesting things for us. So let's look at the pendulum example. So we have two things we're using here. We're using polar coordinates and trigonometry to make the swinging pendulum really easy to program. You press S to stop. Oh, it's hanging forever. It's like when you go on the swing and you really get the top and it feels like forever until you swing back down. Anyway. So here, we have time, increment, base x, base y, radius of the pendulum swing. We have whether it's stopped or not. We have our color scheme again with AOE, clean pond water, beach storm, giant goldfish, and unreal food pills. Creating 600 by 600 canvas. And if not stopped, let's render a thing. So we have our theta here. This is getting our sort of like R value. And then we're getting our increment to time. And we're getting our previous x and our previous y. Our x point and y point, I'm sorry. And then so what we're doing is we have the radius that we have the pendulum to swing, and we just discovered what our current theta should be. So now we're just going to convert that back to normal, or to Cartesian coordinates, to grid coordinates, x, y values, and then use that to draw where the pendulum should be, where the center of the pendulum is, and where the line connecting, the rope connecting the middle of the pendulum to the end is. And so we just did that here. And then the rest of the code is simply setting a fill color, setting a stroke color, drawing a line from the base of the pendulum to where the pendulum should be as we convert it from polar coordinates, and then we're drawing an ellipse where the end should be as well. Right? That's not a lot of code for like something that's oscillating and swinging like a pendulum. And that's because we used the right tools for the job. We used polar coordinates and we used a conversion to get them back to Euclidean space. And we only had to get them back to like Cartesian coordinate space because that's all that P5JS knows. You can't put it into like polar coordinate mode, unfortunately. So we have our pendulum. Now you just have collision detection on it, and you put some blocks here and watch them bounce them around. So at the heart of this also is the fact that we had like this circular motion here. We have sine over time, right? So we have something that's giving us a value on the edge of a circle, but we also did the move of sort of unwrapping it over time, that we sort of like unwrap the circle. You've probably seen in trigonometry where we took the oscillating value of sine and just graphed it over time, which pulls apart the motion and lets us do things like swinging a pendulum. All right. Who knows what kintsugi is? Lots of people raise their hands. Someone who hasn't talked before, please.
Oh,
Yeah,
me?
yeah.
Oh, it's a ceramic art where essentially, like, if a pot or something breaks, you fix it with gold paste.
Yeah. Does anyone want to add more to that? Does anyone have a cultural context for it? Excellent. Okay.
Well, it's a Japanese practice.
Exactly. Yeah. Like paying like respect to a broken thing by fixing it up with something expensive and nice. Right? It's kind of a neat thing. And obviously I'm not Japanese, so if someone knows more than I do about it, please feel free to enlighten us. So let's look at the kintsugi example. We're breaking the space and repairing it. Red and gold on slate. Great. So we're getting a little piece of generative art here. You could use this as like a texture or something in a game, or just have it run on its own. Right? The more you let it run, the more it will, repair cracks in the slate, and the more it will look the more complex and complicated and unreal it will look. But you just start over again. It likes going that way first in these random pulls. Okay, there's one that goes up and around. So let's look at the code for this a little bit. So we have an x and y value. That's sort of like the leading edge of our traversing golden crack. We have the size of each step. We have the time. And we have the time increment that we're giving to noise. We can also stop it and start it by pressing a button. And we have a slate variable and a gold variable where we're storing the slate and gold color. Funny enough, when I just typed in gold as a variable name for the first time, it put the little gold thing by it, like if it was like the actual color in a string, and it will change actually my variable name to be RBG, like obviously something that can't be used as a variable name. So be aware for that. If you see it, just let it be, I guess. Or like you can use something like gold one, like gold, gold. And so here's the values we're using for slate and gold as colors, as color variables, color types. Setting the background to slate. We are setting a noise seed to 10. So if you notice, the first run and second run were exactly the same. See how that one goes and ends like right about here? And the other one follows it, second one follows it. Let's try it again. Exact same. If we change the seed to 11, we'd expect something different. Right, so the power of seeds. Now we're using the width and height of our canvas. Stroke width of 5, stroke color gold. That's all in our setup. The actual drawing, just like with the pendulum, we want to check to see if we should be stopping or not, and we do stopping with the S key. We toggle off, we toggle stopped or paused and not paused, stopped and not stopped with S. And we're controlling whether it stopped or not with a nice big conditional around just about everything in our draw function. And because we're in the business of drawing lines again, lines need a beginning and an end. So we have a new X value, the one we're using this frame, and the one that was their last frame. So we can draw a connective line between the two. Now we're getting a theta value. So we are doing a little bit of polar coordinates here because at the edge of each crack, we want that to be our origin, our center. And then we want to see like which direction do we want to move in and how far do we want to move in that direction. And so we have our value. That's how much we have that set. Or do we set R? Do we set R at the top? Yeah, okay. This is the number of pixels from frame to frame, like the length of the arc. The length of the new portion is 4 pixels. And well, it can be up to 4 pixels. So we're getting at least 0 to 4 pixels. And we're converting, is that true? I might take that back later. We're converting that polar coordinate, given that R value of 4 times the radius, the theta that we just picked from noise times 360. So any value between 0 and 360 will be assigned to theta. And we're getting our new X and Y coordinates back. We're converting polar to Cartesian coordinates. Then we're making sure we're not off the edge of the screen in some way. Because notice when we're off the edge of the screen, we restarted. That's the conditional that takes care of this. So if it's not off the edge of the screen, or I guess if it is off the edge of the screen, we are setting it to temp values. Otherwise, okay. The else, okay, there we are. The else is resetting. And this is giving us our new values. And then we draw a line from previous X, previous Y to our current X and our current Y. Okay, so once again, polar coordinates and noise. One more time for reference. Right, so you can see we stopped it. Here's the edge. And so now at any given time, we're at this tip. And if the tip isn't off the side of the screen in some way, we want to find out which direction we want to move in by getting a value from noise of 0 to 365. So it's going to be a little continuous. And when we have that value, plus the radius that we want to move in, we can convert those into from polar coordinates to Cartesian coordinates and pick our next little spot, our next point that we're extending the line to by 4 pixels. All right, now we're going to try something. Now we know how that's established. Instead of using noise, let's use random. What do you think's going to happen? Any thoughts? Are we getting something as pretty? Nope. I'll take the vague nose. It's just randomly moving around. It's got no plan, and because it's close to the edge, it often goes over the edge. So if we changed the initial values of X and Y, yeah, this is why I did this. That's the X. Let's do the same thing with there. Now we're starting in the middle. Right? And now you can just see it's a random crawl. It's just unpredictable, not continuous. In that flat space that we looked at on the histogram, it's just wherever. And it's like uniform wherever in that space of 0 and 1. Unlike that nice bell curve that we had, which is something near, which is something consistent. All right, so what do you all think about noise now? Noise and random. What do you think about math and angles? Yeah, you got some tools? I know it's probably a bit of a lot. This is probably our heaviest math day so far. But, I mean, it's probably our only, like, real math day. So please study this stuff up. It'll be very useful in your upcoming projects. And it's just an interesting thing to know and understand. Hopefully you've all been just taking a look at these examples that are in the collections for the class for reference. It's kind of nice to be able to get these to you and have them just be in your hands so you can look at them as deeply as you want, play with them as you will. Let me know if you need any more information or you want some clarification on this stuff. I don't know exactly where all of your brains are, but if they're confused in any way, I'd like to help. All right, we didn't quite get to the leaf example. And we only have 4 minutes left. But did any of you take a look at this? I had some people ask about it after class. So you can actually see the sprite sheet for it if you go into Files. You'll see there are two sprite sheets here. The projectiles is one for all of the projectiles that are fired. But the first one is for the ranger. And it looks like this. See if I can make it a little bigger. Right, so we have these various frames of animation. Each one, it's like a flip book. Each one of these is the next frame in a pose, a set of poses, a set of animations. Like you would flip through these like you'd flip through a flip book. You can see there's a lot of these. There's the jumping, here's one for jumping. And you can see jumping up, going up in the air, coming down in the air, the cape billowing, billowing more, billowing even more, billowing a lot, falling fast, right? So each one of these has a meaning. Let's see if we can find another one. Here we're crouching. Oh, we readied an arrow. Now here's one we're actually shooting. All right, so we have all of these individual bits of art that are meant to be used together. In our, with our media computation selves, it's up to us to find these, play these in a sequence over time so that it looks like an animation and happens in the correct context. I kind of like this one, the branch shield. I think that one's kind of neat. We got some beam action here. Someone stole Ash's skill shot. And then we have some hurt and death animations at the bottom as well. So hopefully we'll have some time next class to actually get in and dig into this code so you can see it a little better. If you have any questions about assignment 2, about the labs, let us know. Like I said, I'll be handing out exercise 3, or assignment 3, as soon as I can get it done and out for you all. If I get it out today, that'll be awesome. If I get it out a little later, I'll make sure you have at least 7 days to work on it. I will not short you any days to actually work on the assignment. So I'll refactor the schedule as soon as I get it done. Hopefully it'll be fun. I know a lot of people had a good time with assignment 2. If you would be kind to us and fill out the survey, that'd be great. We're going to record answers and give you another token for turning in a late assignment. So instead of 1, you'll have 2 if you do this. All right, y'all. Take care. Have fun.